Lecture 15, Week 8 of Georgia Tech Group Theory course, lecture Predat Cvitanovic. I feel very sorry you cannot see me, but that's the way it is. In this lecture, we will describe space groups in configuration space. In the next lecture, lecture 16, we will describe Fourier transform of the configuration space. And what's amazing about that is that is how experimentalists actually see and understand crystals. It's irreducible representations of space group. It's not a mathematical construct, it's a real thing. Here is an example. This is a square lattice of atom. And now we will formalize this example by, as usual, defining a bunch of things. Space groups and their symmetry operations. I'm following Dresselhaus' definition 18, point group, which we'll define, and translations which carry crystal into crystal are called space group. For example, this square lattice of atoms, I can move it one square down, one square up, one square to the left, two square to the left, and if it's an infinite lattice, this just being a region of it, lattice map into itself. I can also just turn it by 90 degrees. That's an example of point group symmetry, and turn it again. And this is still a lattice. However, if I turn it by some weird angle, that doesn't fit on the original lattice, so that's not part of a space group. So notation for space groups has to combine the kind of thing that we already know, which is theory, practice, and what happens in our lab. Notation. Rotation by angle alpha, and translation by integer spacing tau denotes a group element. If I don't do anything, I translate by 0. That's the indent. If I rotate by alpha, our usual setting of finite groups, but now it's called point groups. Or if I keep the orientation fixed, so that's identity, and I move by lattice spacing or multiple spacing tau, that's a pure translation. We can write this in a matrix form. We can write alpha tau acting on a 1, 2, or 3-dimensional vector R, some kind of matrix representation of alpha, like rotation matrix, acting on R, plus a translation by a vector tau, which is again 1, 2, 3-dimensional vector. Now what's the multiplication? First, operate by alpha tau, and then I operate by next translation and different angle. First, we apply the rotation onto the vector. That gives us a new vector. Then we rotate that vector by big and translate by the second one. Theorem. All elements, space group G, are of form identity and translation. T is a subgroup of the space group, and it defines the so translation is obvious. We take a thing and we move it, and we move it, but translation without rotating. So that's a subgroup. To show that it's a good subgroup, we have to show that it's a self-conjugate subgroup. If you remember this from triangles, for example, rotation group of 3 elements was a self-conjugate group because reflections didn't take it out. But reflections were not self-conjugate because there were 3 different reflections in the same class. So that's where we have to establish that a translation group is self-conjugate, invariant, or normal. That's my favorite word because, I don't know anybody who is normal, but group theory, we have normal subgroups. And how do you check this? You take an element and you act on it on the right by the inverse. And then you act on it on the inverse of that operation, alpha. So the first operation maps us into rotation. E times r is just the inverse rotation. And the second one rotates the translation. These are different translations. I have to remind you how the multiplication table works. We first apply alpha tau operation on the translation, and then so beta acts on alpha tau, and then we translate. So now you have to be slightly careful to understand how the inverse works. And the inverse says that in rotation, it's just inverse rotation is not a problem. But in the translation, you have to rotate and translate because translations and rotations don't commute. And for that reason, we have to be careful here. So I'll let you check this. Then the multiplication is very simple. Rotations is never a problem. It's just minus alpha times identity. But now you have to remember is that we first act on the translation and then we translate by tau. Then we do it one more time. We have to multiply this vector by that group operation, non-vector. And I get the rotation by alpha from here, rotation by inverse alpha from here, minus sign from here, acting on tau, and then we get plus rotation by alpha on the translation of the element we are looking at, plus tau. This is identity, this cancels. The whole thing is identity times a rotated vector. But the vector that we started with, the translation by t and the translation in the rotated directions, by definition in the lattice, so the conjugation has just given a different translation, which means that it's a self-translations is a self-conjugate group, and that's a nice group that we'll always get rid of first. The main thing to note about space groups is that you cannot write them, even though translation group is a subgroup, you cannot write a space operation just as a direct product of translation and then rotation, because the elements do not commute. So if you look at E, tau time, and rotation, translation by tau, they do not commute. Easy to check. You take them in one order, and you get just rotation by alpha. So in one direction you get that, but if you multiply them in the other order, then again rotation is fine, no problem with that. But now remember we have to first rotate the translation and then add the second translation. And obviously these are not same elements, they don't commute. So the elements don't commute, that's fine, we're used to non-commuting groups. However, we can define a right coset that is a set of all elements, and you multiply t prime, the first guy here, by alpha alpha, and any translation, tau. Multiplication gives me tau. Set of all elements is any translation. So now, even though these things don't commute, the coset doesn't care. For every alpha, R alpha, there is a coset, right coset. You can do this also for the left coset. Works the same. So that implies, as the left and right cosets, I find that the translation group is self-conjugate or normal subgroup of G. And that leads us to the theorem that cosets C alpha, factor, product of two cosets is a product all possible group elements which have rotation alpha or rotation beta in them. Rotations just do the right thing they're supposed to. And the translations are jumbled in some way, T1. But in a corset that exhausts all translations. So these two things, a group multiplication table for rotations, produce an element, and we run over all possible translations on the lattice. Point group. That enables us to define the factor group, space group. These translations quotient it out, and that will be isomorphic, meaning has same multiplication table as the point group. Now what's a point group? It's a group that leaves at least one point untouched. In other words, if you have a triangle and you apply some rotation by 1/3 of 2 pi, that will map vertices around, but this point will be invariant, and that's a property of crystals in 1, 2, 3 dimensions. So now to summarize, what are space groups? A group element or operator of the space group is a rotation and translation. Translations are physics manifest itself through phonons, magnons, etc., which is smooth, long wavelength deformations. Rotations are discrete and physically manifest themselves through anisotropies of crystals. They look different in different directions. You see them through diffraction. And also they have different natural faces. A diamond looks different from a cubic lattice. The translation group defines Bravais lattice by the idea that you can take a piece of it and by translations you can generate the whole thing. It's a normal subgroup of the space group G. Bravais lattice, the configuration space, the physical space, disposition of a crystal. I emphasize this because in the next lecture we will be in a reciprocal space. So they consist of all possible translations in 1, 2, 3 or any number of dimensions. But the index is n-dimensional index, and they're characterized by unidirections. So A1 plus A2 plus A3, where A is a lattice spacing, so the shortest distance between the atoms in a lattice. And N1 and 2 is a triplet of integers that tells you, how far we have to go from origin to get to that point. Now this Bravais lattice gets specified by interatomic spacing, let's say A, B, C, the translations you have to go in 3 directions, and then you have to specify in 3 dimensions the 3 angles between the vectors. It turns out that it's very restricted, the angles that we can rotate by, so the angles between them are, basically 1/3, 1/4 of full rotation. And the simplest of all cells, it's really a one-dimensional one, but nobody understands that, is a cubic one in 3 dimensions, in which A equals B equals C can be set to the same length. And alpha, beta, gamma are 90 degrees. So that's cubic, and that's the picture we showed first. We can talk about things. In 3D, there are only 6 primitive cells. So it's very restrictive. But primitive will mean the tile that tiles the whole space. Unit cell, always a generating region. If you have it, you can tile the space 2, 3 dimensions. Or the smallest generating region, fundamental domain, is the smallest one. So for example, in case of a square, now we have a square lattice, so the unit cell is a little square. If I just slice it around the symmetries and take a region like that, a little triangle, that is good enough. So that's a fundamental domain. Sorry about the light effects, the light ran out in the room. This is not the end of the story, because if you look at the fundamental domain, it contains some atoms. And in particular, disposition of atoms within a fundamental domain is called a motif. If you have a primitive cell, fundamental domain plus the motif, that uniquely characterizes the crystal. Now, there are only 6 of those domains, but by the time we get to crystals, I forget the number, but let's see, there are 232 crystals. So at this point, if your temperament is systematic and you like to enumerate lots of possibilities, you're a crystallographer and you can figure that one out. What we will do, my suggestion is to study 2-dimensional groups. They have a cute name. They're called wallpaper groups. These are all possible ways of creating pieces of wallpaper that will cover the whole wall. Then there is a systematic enumeration of these things. So, CN, then dihedral, but then instead of our D, they like to put C and star. Little twiddle. Then in 3-dimension, the tetrahedral groups. So, like that T, and then there are even octahedral. And these are the point groups which have orders, numbers of elements, 1, 2, 3, 4, 6, which is nice. There's nothing worse than that. This is one of the notation. You'll see it's called Scolinfius, which we'll actually find in practice is another notation called Hermann Mogon, Mogin. And Mogin does stuff like that. You look at, so this is called primitive, P for primitive, and this one is, you say, C for face-centered. Then you put a digit behind this. So you say it's P. And then you count, what's the highest rotational symmetry for this guy. So here it's presumably 4. And here it could be 4 and 8, depending on rotation, C4. Then there is another unit, which is, it gets increasingly more boring. Does this thing have a mirror symmetry? Does it have a glide deflection? It has no symmetry. Let's say if it has mirror symmetry, you put M here. Then, goes on, and it turns out our simplest lattice, square lattice here, in Hermann-Mogan notation, its symmetry is 5, 4, M, M. So the beat goes on, and you look in a detail, and unfortunately I didn't take a color picture. You look in a detail in one of these cells, you might find out that fundamental domain is 1/8, But when you look at the motifs, each of these little guys, they're stuck in here, you might find more symmetry, less symmetry, etc. And that's what various P4MM stand for. And it's basically a classification program. The moment you get a hang of it, it becomes boring unless you need to do it for a living. What's really exciting is what's going to happen next week, because we have to figure out irreducible representations. You might think it's going to be easy because this looks like it has something to do with irreducible representations of rotation group that we already know in great detail for the finite rotations, finite groups. However, there is some trickery that has to be deployed to deal with the translation group. And basically, what's the problem? It's a very awkward, monstrous construction when you look at space groups, because you're mixing addition, translations are additive, with multiplications, because rotations are multiplicative. Everything until now had a multiplicative structure in a group, but here we have to mix them, and what we do is we take an object, we translate to origin, and then we rotate. But why do we have to translate it? And why do we have to choose particular origin? What does that mean? So it's slightly awkward, but it's a necessary evil, because, as you will see in the next lecture, or if you read any of the stuff, irreducible representations are not some silly mathematical abstraction with, square roots of unities and e to the I pi m divided by n and stuff like that. They're the thing that experimentalists actually see, and it's the only way to look at, let's say, graphene and identify it as a single sheet of carbon, hexagonal carbon. And the only way to realize that maybe you have the two sheets of graphene stuck on top of each other, because that you see in the scattering when you shine light or X-rays or whatever is appropriate energy beam that you have to use. They will enable you to see with your eyes, experimentalists, on scale of millimeters, whether the material you're looking is a perfect crystal, what kind of crystal it is, and even whether, if it's not what you want, you might understand the layers and other things about it. So it's amazing, because here it's the irreducible representations which are the physical reality of the problem, and our pictures of atomic lattices are idealizations, because we actually do not see these lattices. We have a rather hard time accessing them. I'm sorry. I'm sure it has been better just to read papers and listen to this lecture, but we do what we can.